Great, welcome to the Exam 1 review webinar. Tonight's information is going to cover stuff for Exam 1, which covers material from Module 1, which is sections 1.1 through 1.4 in your text, and Module 2, which is sections 2.1, 2.2, and 2.4. So, some test-taking tips. Make sure to give yourself plenty of time. This exam should take about 2 hours, but you want to make sure that you give yourself a little more than that if you feel you need it. Take your time, take a break when you need to. Don't stress yourself out because that's not going to do you any good. It's just going to do more harm than anything. So make sure that you give yourself enough time to properly devote to the test. Take your exam in a quiet place, turn off your TV, your phones, any other distractions you have, a place where you can concentrate where you're not going to be disturbed. Have your notes, your book, your exam review with you and ready to go. You can have your textbook open, you can have your notes open, everything is free game for you to use as you go into this exam. Look up each question, study similar examples. It'll give you the ability to kind of have an idea of what you're expected to do as you work on the exam question. Be sure to watch your decimals. Keep 3 to 4 more decimal places than the number requested. So if they say round to 2 decimal places, keep at least 5 to 6 decimal places before you round, and then round down as the final step. Make sure you read the directions carefully, and most importantly of all, good luck. I know you guys are going to be able to do great. So we have some vocabulary. Vocabulary is the name of the game in section 1. So starting off with Module 1 vocabulary, we've got statistics. Statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. In addition, statistics is about providing a measure of confidence in any conclusions. So, when they ask for what a statistic individually is, a statistic is a numerical summary of a sample. Descriptive statistics consist of organizing and summarizing data. Descriptive statistics describe data through numerical summaries, tables, and graphs. Inferential statistics uses methods that take a result from a sample, extend it to the population, and measure the reliability of the results. So the difference between those is the descriptive statistic is a measure of what actually is, and an inferential statistic is an assumption about how it is for everyone based off of what it is for a small section of everyone. Data is the information that we use. So when you have a list of numbers, or you have a list of books that you're choosing from, or you have a list of days of the week, that is all data. So the entire group to be studied is called the population. So the population is the big overarching section. A sample is the subset of that population that is being studied. And then slightly down below that is the individual, which is a single person or member of the population. So the way to remember that is population is the biggest, sample is a small section of the population, an individual is a member of the sample and the population. A parameter is a numerical summary of a population. So it's kind of like a guideline for what the population is. It's a numerical outline of that population. So variables are characteristics of the individuals within the population. So there are things that'll change from one individual to another. And there are different kinds. So you have qualitative variables, or categorical as they're sometimes called, allow for classification of individuals based on some attribute or characteristic. So something that is non-mathematically numerical. So, someone's hair color, someone's eye color, whether they're male or female, what their social security number is. Those are all qualitative variables. Quantitative variables provide numerical measures of individuals. The value of a quantitative variable can be added or subtracted to provide meaningful results. So, ages can be subtracted to find out, the difference in seeing who's older, whereas a phone number can't be subtracted from another phone number and give you any real meaningful result. I mean, you'll get another number, but that doesn't necessarily mean that it's a functioning phone number. Discrete variable is a quantitative variable that has either a finite number of possible values or a countable number of possible values. The term countable means that the value result from counting, such as 0, 1, 2, 3, and so on. A discrete variable cannot take on every possible value between any two possible values. So it's not an infinite number of values, it's a set number of values. A continuous variable is a quantitative variable that has an infinite number of possible values that are not countable. A continuous variable may take on every possible value between any two values. A good way to remember these: a continuous variable is something that measures something. So you can break a measurement down. So you can go from hours to minutes to seconds to milliseconds. You can go from miles to yards to feet to inches to fractions of an inch. And the discrete variable is going to be, you're sitting on the side of the road and you're counting all of the blue cars that go by. 1, 2, 3, so on and so forth. The explanatory variable is a variable that explains what is happening in a particular question. So it's the variable that is directly influencing the other variable. The response variable is the variable that is being affected by the explanatory variable. So the explanatory variable explains what's happening, and the response variable responds to the explanatory variable. One second. So a lurking variable is an explanatory variable that was not considered in a study, but that affects the value of the response variable in the study. In addition, lurking variables are typically related to explanatory variables considered in the study. So it's something that is not directly being studied, but is directly influencing the outcome of the experiment. The levels of measurement. So there are 4 different kinds of levels of measurement. The first one is nominal level. So a variable is at the nominal level of measurement if the values of the variable name, label, or categorize. In addition, the naming scheme does not allow for the values of the variable to be arranged or ranked in a specific order. So this is just specifically naming them. They can't be ranked in any particular order. A variable that is at the ordinal level of measurement if it has properties of the nominal level of measurement. However, the naming scheme allows for the values of the variable to be arranged in a specific order. So building one upon the other. So first one, if something can be labeled or categorized, it's at the nominal level. If those items can be arranged in a meaningful way, then that's an ordinal level because they can be ordered. A variable is at the interval level of measurement if it has the properties of the ordinal level of measurement and the differences in values of the variable have meaning. A value of 0 does not mean the absence of the quantity. Arithmetic operations such as addition and subtraction can be performed on values of the variable. So these are things that can be influenced against each other by adding or subtracting. So like age. A variable is at the ratio level of measurement if it has the properties of the interval level of measurement and the ratios of the values of the variable have meaning. A value of 0 means the absence of the quantity. Arithmetic operations such as multiplication and division can be performed on the values of the variable. So this one is taking it to that next step. If you can, multiply the values and they have meaning, that's when it's at a ratio level. An observational study measures the value of the response variable without attempting to influence the value of either the response or explanatory variables. That is, in an observational study, the researcher observes the behavior of the individuals without trying to influence the outcome of the study. So this is when you put someone in a room with something that they don't like and you watch how they react to it. And you do that with lots of different people to see what the response to that thing is. But you don't directly add or subtract something from the room. That everything is in there to begin with. If a researcher assigns the individuals in a study to a certain group, intentionally changes the value of an explanatory variable, and then records the value of the response variable for each group, that study is a designed experiment. So you're specifically setting things up to try to achieve your results. So you're saying, I think that this is going to happen when I do this, and then you do it and see if it happens. Confounding in a study occurs when the effects of two or more explanatory variables are not separated. Therefore, any relation that may exist between an explanatory variable and the response variable may be due to some other variable or variables that were not accounted for in the study. So that just means that there are outside factors that are possibly influencing it, meaning that something else may be causing the result and not the variable that you're looking at. A census is a list of all individuals in a population along with certain characteristics of each individual. I'm sure you're all familiar with like a national census where you find out, the names, ages of the people who all live in certain places. It's the same kind of thing. It's getting background information for the people that you're studying. So, sampling. So a sample size of n, lowercase n, from a population of size capital N is obtained through simple random sampling if every possible sample of size lowercase n has an equally likely chance of occurring. The sample is then called a simple random sample. Random sampling is the process of using chance to select individuals from a population to be included in the sample. So you have no influence on it, you're just pulling names at random. A stratified sample is obtained by separating the population into non-overlapping groups called strata, and then obtain a simple random sample from each stratum. The individuals within each stratum should be homogeneous or similar in some way. So that would be like grouping all men and all women and then taking certain people from each group. A systematic sample is obtained by selecting every kth individual from the population. The first individual selected corresponds to a random number between 1 and k. So it's kth, kth, and that means that you're choosing random individuals in a specific order of every kth. So if it's 7, it's every 7 people. So you go down the line, 1, 2, 3, 4, 5, 6, 7 is one person, and then start counting again. A cluster sample is obtained by selecting all individuals within a randomly selected collection or group of individuals. So it's like saying, okay, I see all of you people hanging out together in a workplace, so I'm going to question all of you, and you're my sample of the whole workplace. Replacement happens when you pull an individual from the population and then place them back into the population, and you have the chance of pulling them again randomly. So for that one, let's say there are 5 movies on a shelf, and you close your eyes and randomly pick one and you watch it. The next day, you still have the same 5 movies on the shelf, you close your eyes and pick one at random, it could be the same one again because you replaced that movie. Any questions on the vocabulary for Module 1? All right, so an example of explanatory versus response variables. This is something you're going to see coming up in one of your homeworks. So a doctor wants to use head circumference as a variable that is a predictor for weight of a baby. So you look at the head circumference being your explanatory variable because the doctor's hoping that, the smaller their head circumference, the shorter their length, the larger their head circumference, the longer their length. So the explanatory variable is the head circumference, the response variable is the length, and what they're expecting is for that line of data to go straight up on the diagonal, showing that the explanatory variable is directly influencing the response variable. So a sample is a group of individuals from a population, and a variable is one particular aspect of that individual. So if we take a group of 15 people and we want to use height to determine, whether or not where they get a full night's sleep. So we want to say people who are shorter sleep better. The variable in that is not the sample, because sample is the 15 people. The variable is their height, because that's the thing that's varying. Not a problem. On to Module 2 vocabulary. So a frequency distribution lists each category of data and the number of occurrences for each category of data. So it's going to line up and say, okay, between 1 and 5 there were 3 events. Between 5 and 10 there were 7 events. Between 10 and 15 there were 4 events. That's how the frequency distribution works. The relative frequency is the proportion or percent of observations within a category and is found using the formula where relative frequency is equal to the frequency you're looking at divided by the sum of all frequencies. So if we wanted to know what the relative frequency of being somewhere between 5 and 10 in that last example was, you would take the 7, which is the total of the values that are between 5 and 10, and divide it by the total number of values, which is 14, because we had 3, 7, and 4, so 14. 7 divided by 14 is 1/2 the frequency of 0.5. A bar graph is constructed by labeling each category of data on either the horizontal or vertical axis and the frequency or relative frequency of the category on the other axis. Rectangles of equal width are drawn for each category. The height of each rectangle represents the category's frequency or relative frequency. So the height of that bar is what's determining what your frequency is on a bar graph. A Pareto chart is a bar graph whose bars are drawn in decreasing order of frequency or relative frequency. So it's just rearranging the data to show from the highest frequency or relative frequency to the lowest. A pie chart is a circle divided into sectors. Each sector represents a category of data, and the area of each sector is proportional to the frequency of the category. So the way that that should break down is when you finish putting the pie chart together, you should get a total of 100% for each section. So each totaled section added together, the percentages of that section against the whole number of events should be equal to 100%. A histogram is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of the class. The width of each rectangle is the same, and the rectangle. So the difference between a histogram and a bar graph is on a bar graph, the rectangles don't touch each other, and on a histogram they do. And that shows you that the categories are directly connected to each other as they flow from one to the next. Whereas a bar graph could be used for just nominal variables, so they don't need to be connected, because if you're measuring the length of someone's fingers, they wouldn't be connected in any way. You just have one column that would be the length of thumb, one column is the length of index, one column is the length of middle. Whereas in a histogram, it would have to be information that's all flowing from one to the next. So for class limits, the lower class limit is the smallest value within the class, and the upper class limit is the largest value within the class. And the class width is going to be the difference between the two. So let's say we have a class that runs from 0 to, so each class is going to run a width of 1. So we have 0 to 0.99, and then we have 1 to 1.99, and 2 to 2.99. So a stem and leaf plot is another way to represent qualitative graphically. In a stem and leaf plot or stem plot, we use the digits of the left to the left of the rightmost digit to form the stem. Each rightmost digit forms a leaf. So for example, if we're doing something that's looking at the ages of people in a group, you would have a stem of 0 and then 1 through 9, and then a stem of 1 and then leaves of 1 through 9, and a stem of 2 and leaves of 1 through 9, because ages only go from 0 to 9, and then 10 to 19, and then 20 to 29. And you can have multiple leaves of the same number if there are people who are the same age. So let's say in our example we have a 7-year-old, an 8-year-old, a 12-year-old, a 20-year-old, and another 20-year-old. So we would have, our stem graph would look like 0, 7, and then 8. So 0 on one side of a line, and then 7 and 8 on the other side. And then we'd have a 1 on one side of the line, and 2 on the other. And then we'd have a 2 on one side of the line, and on the other we would have 2 zeros. It would be 0, 7, 0, 8, 1, 2, 2, 0, and 2, 0, giving us 7, 8, 12, 20, and 20 as the ages of our group. So distribution. So distribution refers to the way that data is laid out in a histogram. So a uniform distribution exists when the frequency of each variable is spread out across all of the values. So your histogram would have a flat line on the top of it. A bell-shaped distribution would be a histogram that has most of the data located in the middle, so that it kind of peaks up in the middle and tapers off on the end, on either end, and you could draw a bell shape over it. And then you have skewed right and skewed left. That means that there are outlier pieces of data that are leaving the graph to have a tail. And something that is skewed right has its tail going out to the right, and something that's skewed left has its tail going out to the left. So that means when you're looking at the graph for something that's skewed, a skewed right graph is going to have most of its data on the left, and a skewed left graph is going to have most of its data on the right. And then one thing to be aware of is graphical misrepresentations. So there are graphs that can be misleading where they will set things in order where the graph is set incorrectly. So maybe the graph doesn't start at 0, it starts at 200 and only goes to 400. But something that would have a much larger bar from 0 to 2, from 0 to between 2 and 400 would look shorter if it only went from 2 to 400. Also, a lot of the kinds of graphs that you see in magazines, articles, things that are picture graphs, they're not really numerically represented. They're, it's various sizes of pictures or various images that show like the kinds of toppings people like on their cheeseburgers, and one graph is just the burger and it's really small, and then the other graph is a picture of all of the toppings, which makes it look like it would be a lot more people who do that, but then the numbers would be in reverse, where maybe more people like having just a plain hamburger than like having onions and pickles and tomatoes and lettuce and ketchup and mustard and relish and all of that other stuff on their burgers. So you got to be careful when you're looking at the graphs that you see in popular media, because they might be misleading with the pictures. Any questions on vocabulary for Module 2? Not seeing any questions, moving on to the next slide. So, how to use your study guide. So here you have an example of how this study guide is going to break down. So, exam problem number 1, basic statistics vocabulary. Module 1, the homework is in Module 1. It's in the problem set number 1. And it tells you, enter the Module 1 assignment in review mode, go to problem 1, click on the textbook button, scroll through the text looking for the highlighted definitions. And then the qualitative versus quantitative, that was addressed in questions 3 and 4 in Module 1 homework. Question 3 is like questions 5 and 6. Question 4 is like question 10. The whole study guide gives you that breakdown of where the questions are coming from. So an example of problem number 1. A list of observed values for a variable is, and you guys can feel free to type in an answer if you'd like. A list of observed values for a variable is data. This is a vocabulary question, so you'd review the vocabulary list, and like I said, you can find them in your text. sections 1.1 through 1.4. It's the information that's highlighted in like a yellowish beige kind of color. Example problem number 2. Determine whether the variable is qualitative or quantitative. First one, number of flights leaving an airport each year. Is that qualitative or quantitative? Quantitative, that's right, because you can subtract the number of flights leaving this year from the number of flights leaving last year to find out which year had more flights. Number 2, determine whether the variable is qualitative or quantitative. Favorite sport. Qualitative is right. That is a quality of someone, what their favorite sport is. Number 3, age. Yep, quantitative. So age is quantitative because you can add or subtract the numbers to find the difference between two ages and it still makes sense. How about telephone number? Correct again, qualitative, because you cannot subtract two telephone numbers and get a meaningful result. And last one, social security number. Yep, this one's qualitative too, because adding and subtracting two social security numbers is not going to give you any meaningful results. Example problem number 3. Is the random variable x, is it discrete or continuous in the example? So x represents the number of quarters needed in a parking meter. Correct, it's discrete because there's a specific number and you can count them. When x represents the height above the ground when skydiving. Correct, it's continuous. Like I said, easy way to spot a continuous variable is if it's measuring something, and height above the ground is definitely a measurement. X represents the time needed when taking an exam. Now this one can be a little tricky. So while you can count specific hours, the time is a measurement, so it could be continuous. Lastly, X represents the number of movie tickets needed for a family to see the movies. Discrete is correct because there's a specific number that can be counted, and that's the number of people in the family. So you can see discrete, continuous, and discrete. Remember, time is a measurement, so that's an easy indicator of when it might be continuous. All right, example number 4. While shopping, people are asked to perform a taste test in which they drink from 2 randomly placed unmarked cups. They are then asked which they prefer. Is this an example of an observational study or an experiment? Well, I mean, technically you could say that there's some discrete continuous, but generally they're used as two completely specific different descriptors. Discrete being something that can be physically counted, whereas continuous can have up to an infinite number of different responses. So time can be broken down. You could count hours, you could count minutes, you could count seconds, but you could also break it down into milliseconds and microseconds. So you could keep breaking that measurement down and getting it smaller and smaller and smaller, making the differences between people smaller and smaller and smaller. All right, so this is an experiment because the researcher is intentionally imposing treatments on the individuals in a controlled setting. So remember, in an observational study, the researcher has absolutely no interaction with the individual at all. And in this case, they have the interaction of giving them the cups and choosing which liquid goes in which cup. All right, example 5. One night a week, a family has leftovers for dinner. There are 4 people in the family and 4 possible leftover single-serving meals. The family members are Mark, Wendy, Sharon, and Jeff. The servings are tuna casserole, hamburger, salad, and salmon. Mark chooses a hamburger. Can the hamburger be chosen by another family member? Well, the depth of the ocean is one kind of a measurement, and the amount of water is a different kind of measurement. So they would both be continuous variables because you could constantly break the number down, making it smaller and smaller. And so would this be an example where replacement is allowed in this question? Exactly. You guys are right on the right track with this. No, there are single servings, so the hamburger can only be chosen by one person. And this is not a scenario where replacement would be allowed because the person is going to eat the meal and therefore they cannot replace it. Example problem number 6. A radio station asks its listeners to call in their opinion regarding the use of U.S. forces in peacekeeping missions. What type of sampling is used? This is an example of convenience sampling. Great job, guys. The radio station is relying on voluntary responses to obtain the sample data. So it's sampling of convenience. Example number 7. The presider of a guest lecture series at a university stands outside the auditorium before a lecture and begins and hands every 5th person who arrives, beginning with the 3rd, a speaker evaluation survey to be completed and returned at the end of the program. What type of sampling is used? Man, you guys are on top of this. Systematic sampling. The presider is sampling every 5th person attending the lecture. Example problem number 8. In a national survey conducted by the Centers for Disease Control to determine health risk behavior among college students were asked, how often do you wear a seatbelt when riding in a car driven by someone else? The results are as follows. So approximately what number of college students responded most of the time? All right, and how many more college students responded always than never? So to answer that second question, what you're going to do is you're going to take the total number of people who responded always, which is 2,500, and you're going to subtract the number of people who said never, which in this case looks like it's probably about 100 because it's even shorter than halfway between the bars. So when we look at the answer, we'll see 1,200 students because it's in there. You guys were right on there. 1,250, 1,300, that's approximately. So it doesn't have to be exact. So you guys are right in that area. So you're reading this graph perfectly. And then that small little never amount, they're saying it's about 150. So 2,500 minus 150 gives us 2,350. So some of you are on the right path with that. Just remember that to find the difference between the two columns, you take the one column minus the other column, and you want to make sure that you're using the right columns and that you're kind of analyzing the graph a little bit, because we know the middle between the two lines would be about the 250 mark in each section, and this one is a little bit less than 250, so that's how we know. Example problem number 9. To predict future enrollment, a local school district wants to know the number of children in the district under the age of 5. 50 households in the district were sampled, and the head of household was asked to disclose the number of children under the age of 5 living in the household. The results are as follows. Construct a relative frequency distribution for the data. And then they're going to ask you what percentage of the households have 2 children under the age of 5. What percentage of the households have 3 or more children under the age of 5? So to do this, for the first one, what you're going to do is you're going to sum up the total number of households. So the total number of households, add those together gives you 50. And then step 2, divide each individual result by 50. So for example, 16 divided by 50 equals 0.32. So the relative frequencies are shown here. And so then they want to know what the percentage of households have 2 children under the age of 5. So that's specifically the column for 2. So what you're going to do is you're going to go over and you're going to see that the relative frequency is 0.24. And to turn a relative frequency into a percentage, all you do is you take that decimal point and move it 2 spaces to the right, which would make it 24%. And then they want to know what percentage of households have 3 or more children under the age of 5. So you're going to take the relative frequency of 3 and the relative frequency of 4 and add them together to get a relative frequency of 0.08. Move that decimal 2 places to the right and you get 8%. Does everyone see how that was done? Perfect. Example problem 10. The following data represents the fall 2009 students' headcount enrollments for all public community colleges in the state of Illinois. So they want you to first find the number of classes. Six is correct, because if you look under the column number of students enrolled, there are 6 different sections, 6 different categories. And so they want you to find the upper and lower class limits. So let's just do the first one. What's the lower class limit in the first section? Perfect. And what's the upper limit on the very last class? Perfect. And then to find the class width, what you're going to do is you're going to take the limit of one class and subtract the upper limit and subtract the lower limit. So if you use the first one, you would take 4,999 minus 0. So the width for the classes is going to be 4,999. It's not going to be 5,000 because it's not quite 5,000. Because if you look, in order for the width to be 5,000, the first one would have to be 0 to 5,000, and then the second one would be 5,001 to 10,001. So it would have to keep increasing by 1 each time, and it wouldn't look as nice, I guess is the best way to put it. So the width is going to be 4,999 for these. Nope, I was wrong. You guys are right. It's 5,000. You take the lower class limit of 1 and minus the lower class limit of the other. I was wrong. Just goes to show that, you know, everyone has times where they're wrong. It's okay to make mistakes so long as you learn from them. Example problem number 11. A basketball player habitually makes 70% of her free throws. In an experiment, researchers asked this basketball player to record the number of free throws she shoots until misses. The experiment is repeated 50 times. The following table lists the distribution of the number of free throws attempted until a miss is recorded. So to construct a relative frequency distribution, it's going to be same as we did before. And then, what is the percentage of the time did she miss on her 4th throw? What percentage of the time did she first miss on the 10th free throw? And what percentage of the time did she make at least 5 in a row? So these are a little bit harder to get the answers on. So to get the relative frequency, you're going to take the frequency, each frequency, and divide it by the total of all frequencies. And then to get so there's a total number of 50 because the experiment is repeated 50 times. And so if we want to find the percentage of the time that she misses on her 4th throw, we go number of free throws until a miss. So this means that she's missing on her 4th throw, so she's made 3. So we would take the frequency there, which is 9, divided by 50, giving us a relative frequency of 0.18, which percentage-wise would come out to 18%. See, they worded this question all weird. So I apologize, guys. I really hate this question. She's missing on her 4th throw. So the number of free throws until a miss. So on her 4th throw, she has a miss. So that's where the number 4 is. The relative frequency is 0.14, giving you 14%. What percentage of the time did she miss the first miss on the 10th free throw? So you come down to where the number of throws until a miss is 10. The percentage is the relative the percentage is 2%. And then what percentage of the time did she make at least 5 in a row? So remember, at least 5 means that she made 6, 7, 8, 9, or 10. So we go to 6, just 3, plus 0, plus 1, plus 0, plus 1, just a total of 5, divided by 50 is 0.10, equals 10% of the time she made at least 5 3 throws in a row. So the way that this is worded means that in order for her to make 5 3 throws, the first time she makes 5, the number is 6 because she misses on the number 6 shot. Nope, you wouldn't include 5 because what that means is that the column for 5 means that she made 4 and missed on number 5, so she didn't make 5. Example problem 12. Is this graph misleading, and what could be done to improve the graph? Yep, that's right. You could remove the word massive. The fact that the graph starts at 79,000 and not 0, that's another one. The fact that the bar is 4 times larger is true, and that happens because of the spacing of the numbers on the left. So if we were to start at 0, these bars would look much closer together, and because each line, instead of representing, $1,000 or $5,000 of increase, they're representing a difference of $500 between each line, which extends the graphs, which makes it look like 1999 is a lot bigger than 1998, when really it's only $2,000 difference. So the base of the y-axis should be at 0 is the best way to improve this graph, because then you'd see the length of both of the bars, and they would look much similar because they would have to, the gap between spaces would have to shrink because the bars would be much larger. And so if you haven't yet, please fill out the attendance form before you leave. That is the end of the review session. So good luck. I know you guys can all do it, and just give yourself time, have a little bit of patience, and don't feel like you have to rush through it. That's the best advice I can give you, is don't rush. Have a good night, everyone.